Hello and welcome to Empowered Learning. This video is the third video in the video series for finding zeros of polynomials of high degree. So before we get into the examples of showing you how to use rational zeros theorem and, when appropriate, the Carter's rule of signs, as well as the skills of synthetic division to be able to help factor down our polynomials of high degree, we first want to categorize the types of zeros that polynomials actually yield for us. And so in general, we have two types of zeros that polynomials yield for us. We either have real number zeros or we have complex number zeros, okay? And so with the real number zeros, of course, going back to basic arithmetic here, one of the things that you learned, may have forgotten, but you learned this, is the difference in between the different types of numbers within the real number set. And on a higher level, we could just basically say that the real number set consists of numbers that we can express as fractions and numbers that we cannot express as fractions. And so rational numbers are numbers that we can express as fractions. Irrational numbers are numbers that we cannot express as fractions, and they're real, okay? And so these are all the numbers that we're used to dealing with in everyday life. So we know that our rational zeros, they do not come in conjugate pairs. So they don't follow the irrational or complex conjugate pairs theorem, okay? And we use the rational zeros theorem to be able to find out for a particular polynomial if any of those particular numbers actually work as zeros. For the types of zeros that come in conjugate pairs, of course, we have the irrational and the complex ones. And we discussed that in the part 1 video that talked about the irrational and complex conjugate pairs theorem. And so again, we can't use the rational zeros theorem to find these two types of zeros here. So when we do our examples, the first thing that you'll see that we do is apply the rational zeros theorem so that we can actually find what rational ones we can, and then from that, use what we find to factor down our polynomials and hopefully get to a point to where what we end up with, we could factor using other factoring techniques that we know to see, hey, are those zeros going to be complex, or are they going to be irrational, or we're going to have a mixture of both. So that's kind of the idea here. So next, we'll get into doing some examples. So for the examples that we are going to do that follow, the directions will be the same for each and every one of them. And so when we put this all together, the first thing that we want to do is find what rational zeros we potentially have for a polynomial. And we're going to use the rational zeros theorem for that. And then using this theorem, we're going to find out which of those numbers in that list of potential zeros are actually zeros. From there, we're going to find out what our other zeros are. And when I mean other zeros, I mean that they're either going to be irrational and or complex. And then we're going to write our polynomial as a product of linear factors. So for instance, if I had, let's say, x plus 3 times x plus 2, of course, I know that function-wise, that would just multiply out to be x squared plus 5x plus 6. All right, and I'm trying to erase this right here. We'll just do it like that. So the point that I'm trying to make here is that we know that this multiplies out to be this. This is the form of this particular polynomial here in factored form. And what number 3 states, write f of x as a product of linear factors, this is what we mean, okay? And then, of course, the last thing that we want to do is sketch the graph of this polynomial. So for our first example, we look at the polynomial that we're given, and we see that is of order 3. And we notice that we don't have any factoring techniques that we know of that will allow us to be able to factor this right away. Okay. So most of the factoring techniques that we know of is for quadratic equations. With quadratic equations, we know trial and error method, we know factor by grouping, divide and squeeze. Some of you know how to factor via the boxes or whatnot. So none of those methods work here. So what we start off doing is, since none of those methods work and we have a polynomial that is higher than degree 2, we're going to use the rational zeros theorem to kind of kick us off. And so again, the rational zeros theorem says that if we have a polynomial where every coefficient can be written as a fraction, so here we have understood 1 that can be written as a fraction, we have negative 12 that can be written as a fraction, and we have 16 that can be written as a fraction. So this particular polynomial passes the test of using the rational zeros theorem. So here, what we're going to say is the list of potential zeros will be all the factors of our constant coefficient. And in this case, all the factors of 16 are going to be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, and plus or minus 16. And we'll take all of that and we're going to divide it by all the factors of 1, which is just going to be plus or minus 1. So in this case, it's just going to be the list of numbers that I have here. So of course we'll have this divided by plus or minus 1, and that will just give us this list here back again. Okay. All right. So now that we have that, what we would do in an antiquated world is we would actually take each and every one of these numbers, and of course you got 2, 4, 6, 8, 10 numbers, and you would use synthetic division to figure out which of those 10 numbers would actually be zeros. Okay. Now, here's where using technology could actually help shorten this process a lot. We could do synthetic division 10 times, but that's a lot of writing. And the thing is, we want to use synthetic division judiciously. We only want to use it once we know what we have actually works. So what I'm going to do is show you how we could actually use a graphing calculator, and I'm going to use a TI-84 to be able to let it tell me by applying the rational zeros theorem if any of these numbers work, and if so, which ones. So I'm going to bring my graphing calculator here. And what I'm going to do is I'm going to type in this particular function. So to do that, I know that this button here with the X and the T and the theta and the nu, that's going to be my variable button. So I'm going to do that, raised to the 3. And then I will do the right arrow here to get out of the exponent. Then minus 12x, then plus 16. Okay. And so here I press the Y equals button here to get to this point. So I'll go to second quit here for a second. If I press this button, that's how I got there. So from here, then the next thing that I want to do is I want to set my window. Okay. I'm not interested in necessarily graphing this function. What I'm interested in is using the tools to allow me to be able to evaluate this function at different x values. And so there's a couple of ways we can do that. But the first thing I want to do is set my window. So for my window here, I see that it's set for the x values, x min and x max, to be negative 10 to 10. That is the standard. The y min and y max also at negative 10 to 10. We don't really care about the y max here, but we do care about the x min and x max. So what I want to do is make sure that all the numbers that are in my list, okay, And of course, I'm going to move this away for a second. If you notice, all the numbers that are in my list are from plus or minus 1 to plus or minus 16. So here, what I want to do is, I know that the smallest number in this list is going to be negative 16. That's the smallest number. The largest number in this list is going to be 16. So when I set my window here, what I want is I want to be able to fit negative 16 all the way to positive 16 in this list. So what I'm going to do is I'm going to type in a negative 20 for the x min, and I'm going to type in a positive 20 for the x max, just to give myself a little room. Okay, so from that point, then I have everything that I need. One way, and this is my preferred way of actually trying out these numbers here, is I can go to second and then press the trace button. When you do second trace, you're actually in calculation mode. And what you're trying to do is tell your calculator to calculate, some type of values. And so here you got value, 0, min, max. For what I want us to do here, let's just do value, okay? And so if you notice here, and I'm going to slide this over, if you notice here that yes, it has graphed it for us, but again, we're not necessarily worried about that. What we want to do here, and I'm teaching you this skill, because here you can kind of see, all right, negative 4 is going to be 0, 2 is going to be the other. But there are some instances where you deal with polynomials where it's not this easy to see. And so we need to be able to do a more systematic process of finding the zeros here. So here, what we would do is just start off. And I'm going to start with all my positive values. So I'll plug in a 1 here. Let's see, I lost that. So let me do it again. Second, calculate value. And then here I'll plug in a 1 and then enter. And as you see, I know that since this y value is not a 0, then 1's not a 0 of the polynomial. So what I do now that I'm in the calculation mode, I just try the other numbers. So here I go 2, enter, and you see that 2 works. 3, enter, 3 doesn't work. 4 doesn't work. 8 doesn't work. 16 doesn't work, okay? So what we see here is that x equals 2 is a 0, and it's a positive, okay? Now, if we tried all the negative numbers, so negative 1 doesn't work, negative 2 doesn't work, sorry, not negative 3. I'll go ahead and do that one in, but negative 4, that one does work. And then we have negative 8, doesn't work. Negative 16 doesn't work. So we see from what we found here that the only 2 that worked were going to be negative 4 and 2, okay? So noting that, now we're going to actually write that down. So because of this, our actual rational zeros are going to be x equals negative 4 and x equals 2. And so what this lets us know is by the factor theorem that x plus 4 and x minus 2 are factors of f of x, okay? Now, what this tells us is that f of x is now going to be x plus 4 times x minus 2 times something else. And so here is where we want to use synthetic division to help us factor down our polynomial so that we can find out what that last linear expression will be. Now, before I get into that, how do I know that I'm going to have a linear expression? by definition, since my highest exponent, which is the degree of the polynomial, is 3, I know that I have to have 3 zeros, okay? So here I have 2 of the 3 that I'm looking for accounted for. So since I have 2, I know there's going to be 1 more. Since I know that I have to have exactly 1 more, according to the irrational conjugate pairs theorem and the complex conjugate pairs theorem, I'm not going to have that additional 0 be either irrational or complex. And that's because if I have exactly 1 0 left, it can't be a complex number or an irrational one, because remember, they come in pairs, okay? So we know this is going to be another rational number, okay? Now, just to kind of let the cat out of the bag here, I'm actually going to show you how we can fall into this answer without knowing it. We're going to bring this back here. Notice that at x equals 2, this bounces off of the x-axis here. And so if you're studying this, then you've probably also studied what the concept of multiplicity is. And so what this graph is trying to tell us is that the multiplicity of our 0, x equals 2, is actually even. And it has multiplicity 2. So we're going to see that our last 0 is just going to be x equals 2 again, okay? I'm going to show you how we can actually see that through using synthetic division. Because again, the way that I'm doing here, we're acting as if we don't know what the graph looks like, okay? So for synthetic division, we'll start off when x is equal to -4. And so I'm going to write my coefficients here. So I have 1. I don't have an x squared term, so that's going to be 0 there. I have an x term coefficient, which is -12. And of course, I got 16. Set this up, come with my remainder box, pull down this 1, and then -4 times a positive 1 is -4, add. Then repeat, -4 times a -4, positive 16, and then add the -12 plus 16 to get 4. Then -4 times a positive 4 is a -16. We add and get 0. And again, this is what we were expecting. So this is telling us that f of x at this point can be written as x plus 4 times, and down here we know that since we had a polynomial of degree 3, divided it by a polynomial of degree 1, this is going to be my x squared coefficient, x coefficient, number coefficient, okay? And so this would be x squared minus 4x plus 4. Again, we know that if we were to factor out the x squared minus 4x plus 4, we would end up getting x minus 2 times x minus 2. I'm going to purposely not do that here because I want to show you how we use successive synthetic division to be able to factor down our polynomials here. Because we will have examples to where it won't turn out to be this easy and we'll need to do that. So I'm going to go through that process now. So here, when x is equal to a positive 2, I'm going to set up again. And so now what's different is that we're going to take these coefficients and funnel them down here. And so this is how we actually factor down our polynomials. So we'll say 1 minus 4, 4, remainder box here. And then we're going to bring down the 1, and then we start that process all over again. So 2 times 1 is 2. We add, get minus 2. 2 times -2 is -4. Add, get 0. And again, zeros are what we are expecting here because -4 and 2 were zeros. So from here, what we see is that f of x is equal to x plus 4, which came from here. We know that x minus 2 was a factor because we stated that here. From knowing that this was an actual 0, we know that that was a factor. And of course, that's what this means here, that we're actually dividing by x minus 2. And then, of course, the result here, you see that this is coefficient for the x term, coefficient for the constant term, and thus that ends up being the other x minus 2. So this is how we can use synthetic division successively to be able to factor down our polynomial. So now that we have this, we know that f of x is just going to be x plus 4. That didn't turn out too well, so let me erase that. So that's going to be x plus 4, and then this is going to be x minus 2 squared. And so now that we know what our zeros are, we're going to list those as well as list what the other zeros would be, and then we're going to graph our polynomial. So our rational zeros here are just going to be x is equal to -4 and 2, where 2 here is going to be a double root. Our other zeros, which means do we have any irrational or complex ones, doesn't apply. What is our function factored out as a product of linear factors? This is what that looks like. And then finally, we need to graph what this particular polynomial is going to look like. And so now we're going to go back to concepts that if you're studying this, you've probably already learned it. And so here we know that if we have x-intercepts or zeros at -4 and 2, corresponding multiplicity for this particular 0, which goes along with the x plus 4 factor, is 1. And for the x equals 2, 0, corresponding factor has a multiplicity of 2 because the factor shows up twice. And so what we need to know is whether when we draw our graph, is this particular function going to cross through or touch or bounce off of the proper term is be tangent to the x-axis. Okay, so whenever multiplicity is odd, it crosses through. Whenever multiplicity is even, it's tangent to or it bounces off of the x-axis. So here at x equals 2, we have this 0, and at x equals -4, we have this one. And we know that at x equals 2 is going to bounce off of the x-axis somehow. Now, to figure out the rest of the shape of the graph here, one of the things that we need to know is the degree of the polynomial. Well, we already know that the degree of our polynomial was 3, but we can add up the multiplicities here to figure that out. We also want to make sure that we know what the leading coefficient is for our polynomial. And so I'll go back here and we see that our leading coefficient here was a 1. So we're going to use that information to help us to be able to graph what the end behavior of our polynomial is going to look like. So we take this, and we see that our leading term would just look like 1 times x cubed, or simply x cubed. Now, we know that x cubed is a function that looks like this, so that means the end behavior of our polynomial is going to be like this, meaning as x approaches positive infinity, y approaches positive infinity. And as x approaches negative infinity, y approaches negative infinity. So now that we have all that squared away, then here we just go from left to right, and knowing that a polynomial function is continuous, we just note what we need to about the zeros and then sketch the graph. So here at x equals -4, since the multiplicity is odd, we know that the graph has to come from down here and cross through. So graph's going to cross through like this. Okay. Now, for this particular zero at x equals 2, we know that the graph has to somehow get from up here, find its way back down, and then go back up. And of course, the multiplicity being even supports that. So we know that since the graph is above the x-axis before it gets to this particular x-intercept, graph's going to have to bounce off of the x-axis like this. Okay. So knowing all that, we now know what our corresponding graph is going to look like. And so essentially the graph is going to start down here, cross through here, bounce off, and then come back up this way. Okay. And to make a long story short, that is what our graph is going to look like. Now, notice I haven't drawn the graph exact because I know that my y-intercept here would actually be at the point 0, 16. And I know that because if I look back here at my original function, my constant term here is 16. And when x is 0, I know that my y value is going to be 16. And by definition, that is the x-intercept. So if I was going to draw this to be exact, what I would have to do is kind of change the scaling of this particular xy plane here to make every unit here be unit to 2. And so I could say 2, 4, 6, let's say 2, 4, 6, 8, 10, 12, 14, 16, and actually draw my graph up here. Okay. And so in that case, the graph will kind of come up here like this, cross through right here, and then come back and bounce down and then go back up. That's not necessarily that important. The important thing is that you see the connection in between how the graph of the function looks and the process of finding the zeros and factoring down the polynomial. Okay. So that is our first example. We'll do a few more here just to give you more practice. So for our next example, we're going to do the same thing. We see that all of our coefficients here are numbers that can be written as fractions. And here, since this has 4 terms in it, the first thing that we would try to do is see if we can do factor by grouping. Okay. And of course, to do that, the common factors in between the first 2 terms, if I was going to apply factor by grouping, common factor between the first 2 terms is x squared. And I would just get 2x plus 7 here. And the greatest common factor amongst the next 2 terms is just 2. And of course, here we see that we have a problem because if factor by grouping worked, then that means that what is inside my parenthesis for both of these would be the same. Since it's not the same, then I know this is not going to work. So I'm only left now with using the rational zeros theorem to possibly help jumpstart me to be able to factor down these polynomials. So that's what we'll do next. Okay, so now that we know that only the rational zeros theorem will probably work for us in this case, we're going to go ahead and set that up again. So rational zeros theorem gives us the potential zeros. And so in this case, all the factors of 8 are going to be plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. All the factors of 2 is just plus or minus 1, plus or minus 2. And so now to get the total list, here I'm going to start by just using 1 and divide all of my numbers in the numerator by the denominator 1. So that's just going to give me plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. plus minus 4, and then plus or minus 8. So now we're going to do the same thing with the 2. And so now what's in my list is going to be plus or minus 1/2, plus or minus 2/2, which is just 1, plus or minus 4/2, which is just 2, and plus or minus 8/2, which is just 4. And again, since I already have a positive plus or minus 1, plus or minus 2, plus or minus 4, I don't have to write these again. Okay? So I see that my list of possible zeros is just going to be plus or minus 1, 2, 4, 8, and then plus or minus 1/2 here. Okay? So we'll go ahead and get rid of the rest of this since we already know what our list is supposed to be. So now that we know what our list is, again, we're going to bring in our technology to be able to see which of these zeros, if potential zeros, will actually work. All right, so bringing in our graphing calculator again here. You see I've already typed in the function again to save us a little bit of time. So the main thing here is that we want to make sure that our window is set to where the x-min and x-max is large enough. And we see that since the smallest number will be -8 and the largest number in this list is +8, that works. So we're just going to go ahead and do second calc as well, and then press 1 for value. And then from here, we'll just try these out. So I'll start with the positive ones. 1 doesn't work. 2 doesn't work. 4 doesn't work. 8 doesn't work. And -1/2, sorry, +1/2. Let me clear that. +1/2 doesn't work, okay? So we know that even though we see this graph here is giving us a zero that's going to be positive, we know it's not rational, okay? So we know that there's going to be some kind of irrational zero that's going on with this, okay? All right, so let's try the negative ones now. So -1, -2. Oh, we have 1. So we see that -2 actually works, okay? So we have -2 that works. So we'll try the rest of them to see if we have any more. So -4, -8. Of course, those didn't work because we see that from the graph here, but let's see if -1/2 shouldn't work either, okay? So what we see here is that we only have one zero that actually worked out of this list, and that was x equals -2. So we'll write that and use that to be able to factor down our polynomial here. So we have actual rational zeros will be at x equals -2. And what this implies is that x plus 2 is a factor of f of x. And what that implies is that f of x is going to be equal to x plus 2 times something else. And we got to figure out what that something else is. And so here's where we use the synthetic division to do that. So using our synthetic division setup, we know that the actual zero here is going to go in this spot, and we're going to write all of our coefficients here. So we have an x cubed, x squared, x, and then single number coefficient. So everything works out there. We bring this number down, and we just do the process of successive multiplying and adding. So negative 2 times positive 2 is a negative 4. Add, or 7 minus 4 gives you 3. Then do it again. Negative 2 times a positive 3 is a negative 6. And then add. And then negative 2 times a negative 4 is a positive 8. And then add. And so, of course, this just verifies that negative 2 is a 0. But the important thing here is that now we see that our quotient, we have an x squared term, we have an x term, and we have a constant term. Because again, we took a polynomial of degree 3, divided it by a polynomial of degree 1 to get a polynomial of degree 2. And so this shows us here that f of x is just going to equal x plus 2 times, and then this will be 2x squared plus 3x minus 4. And so now our goal here is to actually factor down this. And of course, we could do that by just setting that particular quadratic expression equal to 0 to see if we could actually factor it down. If we can't factor it down, then we have options of either using the completing the square or quadratic formula methods of being able to find out what the corresponding zeros are. Because remember, the first thing that we wanted to do in all of these is figure out what all of the zeros are, and we want to split that up in between the rational ones, which we see that this is the only rational one that we have. And so because of that, we're assuming here that this quadratic expression may end up giving us either complex or irrational conjugate zeros. And so we'll actually try to figure out what those zeros are to be able to see them. All right, so giving us a little bit more room here, come here and say let 2x squared plus 3x minus 4 equals 0. And again, the reason why we're doing this is because we want to find out all the zeros of the polynomial, and there are 2 additional zeros here that will, 2 additional values of x that will make our polynomial go to 0, and those are the other 2 zeros. It turns out for this, you're not going to be able to factor it using traditional quadratic factoring techniques. So we're going to use a quadratic formula to be able to do it. Okay, so using that, we know that our a in this case is 2, our b is going to be 3, and our c is going to be negative 4. Okay, and I apologize for the pen kind of dragging a bit here. So I'll try to write this a little bit neater. Okay, so here we know that this is minus b plus or minus b squared minus 4ac. All that over 2a. And of course, our b here is 3. So this will be 3 plus or minus 3 squared minus 4a, which is 2, and c, which is negative 4. Take all of that and divide it by 2a. This would be a negative 3 plus or minus square root of 9 plus 16 times 2 is 32. All of that over 4. And this is going to give us negative 3/4 plus or minus square root of 41 over 4. Okay. And so since square root of 41 is what we consider to be an irrational number, meaning a number that we cannot express as a fraction, we see that both of our zeros here are going to be irrational conjugate pairs. So our other two zeros actually ended up being irrational conjugate pairs here. So now that we know that, we can now say that our function can be factored down as x plus 2 times, and so here, since our first zero, and I'll write it this way, this first one here is going to be negative 3/4 plus square root of 41 over 4. And the second one is going to be like this. And that should be a minus, not a plus, so I'll change that. And then this is going to be an x minus, and then the first one would be negative 3/4 plus square root of 41 all over 4. And the next one would be x minus negative 3/4 minus square root of 41 all over 4. Okay, so that is what our function would look like if we factored it out as a product of linear factors. Now, of course, I could clean this up here, but what I'm going to do to help us to be able to draw the graph, I'm going to keep it in this form here and find out, well, what is negative 3/4 plus or minus square root of 41 over 4, okay? So here I'm just going to do this here just for the purpose of us having to graph this. So we're going to bring back in our calculator here. And let's calculate what these values are actually going to be. So if we go, just hit clear, second quit. If you're following me with your calculator, then you'll see that you get to the main screen here. And so all I'm going to do is do parentheses, negative 3 divided by 4. And then this will be plus parentheses. And again, I'm doing this just to separate. Don't necessarily need the parentheses for all of these. Square root of 41. And then I'm going to take that and divide it by 4. Okay. So if I get that, I get approximately 0.851. Okay. And if we do the same thing again here, I'm just going to copy this and just change the sign so I can avoid having to type that all over again. Say I get a negative 2.351. So this will be approximately the same as x minus 0.851. And the second one here would be x minus negative 2.351. Okay, and of course this minus a negative here would be the same as addition. So what I'm going to do is just erase all of that and just simply write this as just x plus 2.351. Okay. Now, one thing that I want you to notice here as we get ready to draw the graph of this is that notice that we have 3 separate zeros, and all of them are real number zeros. Okay, we don't have any complex ones. Of course, these two here, approximate wise, are our complex, not complex, but our irrational conjugates. But we have 3 separate real number zeros. Okay, and that goes along with what this tells us, is that we had to have 3 zeros, and we see that one of them came by themselves as a rational zero, because that's where that one was. The other 2 came out to be complex conjugate, irrational conjugate pairs. Okay. Now, the point that I want to make here is, do you see how for the zeros here, and I'm going to list them. So our x-intercepts / zeros. Notice that we have zeros at -2.351. We have one at -2, and we have one at a positive 0.851. These 2 zeros are really, really close to each other. Okay. And I'm going to go back to the graph with the calculator to kind of show my point here. So let's go back to the graph of this, and I'm just going to say graph it. And notice how, if we look here, that this looks like that we have 1 0 here at -2, and that it has a even multiplicity, meaning that it has a double, that its multiplicity is 2, and is going to bounce off of the x-axis, kind of like how we saw in the first example. But we see that that's not true. What we're actually seeing here is that there is 2 zeros that are really close together. So this graph really just kind of skirts, it hits the x-axis, it skirts over just a little bit, and then comes right back down. Okay. Now, part of the reason why we teach this method of factoring down polynomials is for you to be mindful of stuff like this that happens. Okay. If we were just looking at the graph of this particular function and looking at it blindly, then we would think that, yes, we have a 0 at x equals -2, and it has even multiplicity. It's just bouncing off the x-axis here. But that's really not the case. Okay. And of course, if we zoomed in, we would actually see that. And so do you see how here, trace off of that, do you see how here, how it just barely crossed the x-axis, went over, and came right back down? And again, if we don't have these kind of analysis techniques that we're teaching here, we're not going to be able to know that unless we know to actually zoom in on the graph. And the thing is, you got to know to be able to zoom in on a graph if you know the actual zeros you're expecting to get. So again, this is another reason why we teach these techniques here, so that you're not fooled by what your graphing calculator tells you. Okay. Your graphing calculator is there to actually enhance what it is that you already know, but you still have to know something to start off with. Okay. All right. So now that we have that, we know what our function would basically be factored out to be. We're going to follow the same procedure that we did last time to graph this polynomial. So here, the multiplicity for all 3 of these would just be 1, because each factor shows up exactly 1 time. And of course, that means that all of these are going to cross. We know that our leading term here for our polynomial, we go back to the beginning, looks like this. And of course, this 2 here is what our leading coefficient is, and our degree n, that's going to be 3. So basically, for a very large positive and large negative, meaning the more negative you get, it's going to look like the graph of 2x cubed. And of course, the graph of 2x cubed is going to have in behavior like this again. Okay. Now, if we plot those zeros, one of those zeros, if I just do these in half units here, so I'm going to say this is -5 and 5 here. So if we do half units, then this will be 0.5. So about right here would be 0.851. If I do -2 here, so it'll be -1, -2. And then you'll have another zero that's kind of close to be about right there. Okay. And again, since all of these cross through the x-axis, we would have our graph cross through here, cross through there, and then cross through there if we're going from left to right. And so our resulting graph would look something like this. So our graph will come down, come up, come back down, and then come back like this again. Okay. And last thing is, we know that our y-intercept, if we looked here, it is at -8. So here we wanted to be very formal here. Of course, I didn't tell you what the units were on the y-axis, but let's say if we wanted to do these on the y-axis in units of 8, then where we crossed here would be the 0.08. And so in general, that is what that particular graph looks like. Here is what the polynomial will look like in approximated factored form. This is what the exact polynomial looks like in factored form. And of course, if we wanted to simplify things, we could distribute, the subtraction sign to both terms here and distribute it there if we like. Okay? And of course, our actual zeros, here are our two irrational conjugate pairs. Those are two of our zeros. And then of course, the last one here we found was x equals -2. And that was a rational zero. So now we'll go into our last example for this portion. Okay, so for our last example, we will try to do the same thing that we did for the other two examples to figure out what the zeros are for this particular polynomial. Rewrite it as a product of linear factors and then try to graph this particular polynomial as well. So again, we have multiple terms here, way more than 4. So we know that the only chance we have of being able to factor this down is by using the rational zeros theorem. So here, we'll look at all the factors of the last term, which is going to be ±1, ±2, ±4, and then all the factors of the leading term, which is going to be ±1 and ±5. So from here, of course, dividing everything by 1 will, of course, give us ±1, ±2, ±4. And then if we do the same thing by dividing everything by 5, then we're going to have ±1/5, ±2/5, and ±4/5. Okay. And as you notice here, we don't have any zeros here that repeat themselves. So we're in a situation here where we need to actually try all of these zeros out. And so we have 12 in all. Again, we're going to use technology to help reduce the actual amount of work that we have to do. And once we know which of these zeros, if any, work, then we'll use synthetic division to be able to factor down our polynomials from there. So bringing in our technology again, I've already typed in what this particular function should be inside our calculator. So we're going to do the same thing again. We see that our largest and smallest numbers here are going to be 4 and -4 respectively. So our window, remember in the last example, we zoomed in, so I'm going to have to change this window here. And I'm just going to move it to -20 to 20 again. Okay. Now, I haven't mentioned this yet, but I'm going to go ahead and demonstrate this now. What happens whenever we try to evaluate our function at a value that doesn't fit within this window here. So I'm going to do second calc for the value again. And let's say I typed in the number 30, which is outside the range of -20 to 20. And so you see here how it says error invalid. And so what that's basically telling you is that, A, you picked a value that's outside that window range. So that's why I was telling you that we needed to be able to set this range here and know what type of numbers we're going to be plugging in to start with. Okay. So now that we know that, we're going to go to second, trace again, value, and then we're going to type in all these numbers again, see which ones work. So we're going to do 1, enter. Okay, so we see that 1 works. So that's a good sign. 2 doesn't work. 4 doesn't work. And then 1/5 doesn't work. 2/5 doesn't work. And 4/5 doesn't work. So now we'll run through all of our negative ones. So -1 doesn't work. -2 doesn't work. All right, so -4 doesn't work. -1/5. That works, so we got another one. So that's good. So we'll keep note of that. And let's see, -2/5 doesn't work, and -4/5 doesn't work. All right, so the good thing is that we did find 2 zeros that work. The bad thing is that we don't know what the other 2 are. And since they're not in this list of rational numbers, then they're probably either going to be both irrational conjugate pairs or complex conjugate pairs. So we'll go ahead, move this, and we'll note what we found. So our actual rational zeros going to be x equals 1 and -1/5. Okay, and so what this tells us is that x plus 1/5 and x minus 1 are factors of f of x. And what this tells us is that f of x is going to be x plus 1/5. Let's try to make that look a little bit cleaner. Times x minus 1. So f of x is going to be x plus 1/5 times x minus 1 times something. And again, we're going to use our synthetic division to help us to be able to figure out what that something is. So we'll start off with the fraction. We'll start off with that particular 0. And we'll write all of our coefficients. So we got 5, -4, 19, -16, and -4. Let's double check, make sure we got all those in. And then we'll pull down our 5. And then we'll do a series of multiplying and adding. So if we take -1/5 and multiply it times 5, we just get a -1. And then we add. If we get -1/5 times a -5, we get a +1, and then we add. We get a -1/5 times 20. That's the same as saying a -20 divided by a +5. That gives us a -4. And then we add the -16 and -4 to get -20. Here, -1/5 times a -20 is a +4. And then we add and get 0. And so from here, what we see is that f of x is going to be x plus 1/5. And then what remains here, since we start off with a polynomial of degree 4, and we divide it by a polynomial of degree 1, we know this starts off being our x cubed term, x squared term, x term, and numbers term, okay? And so I'll just go ahead and write this. We don't necessarily have to write all of what I'm writing here now, but I want you to be able to follow how we started from the very beginning to factor down our polynomial here. Okay. Now also notice that all of these terms here have a common factor of 5, and we're going to deal with that later. I'm not going to deal with it right now, but we are going to eventually address that. Okay. All right. So now that we have that, we're going to set up our synthetic division again. We're going to do that successive division, synthetic division that I told you about. And so here, what that means is we're going to use these coefficients in the next round of synthetic division that we do. So here we have 5, -5, 20, -20. And we do the process all over again. So 1 times 5 is 5, get 0. 1 times 0 is 0, add and get 20. 1 times 20 is 20, add, get that. So now what this tells us is that we can say this is x plus 1/5 times x minus 1 times, and so again, this second round of synthetic division starts off with a polynomial of degree 3. We divide it by a polynomial of degree 1. And so this means that we're going to have x squared term here, x term here, constant term there. So this is just 5x squared plus 20. Okay. So now at this point, we're going to deal with the common factor of 5 that we saw up here, okay? So notice that what we're left with here also has a common factor of 5. So we could rewrite what we see here this way. And I'm going to take that 5 and factor it out. And if I have that, I'm going to get x squared plus 4 here. Now, since multiplication is commutative, and that's just a very fancy way of saying 2 times 3 is the same thing as 3 times 2, I can multiply any of these in any arrangement that I want. So here what I could do is I could shift my 5 to be here and multiply it times the factor of x plus 1/5. And then just rewrite everything else as normal here. So if I do that and distribute my 5 to this first factor, then what I end up with is 5x plus 1 times x minus 1. And then for here, I would have to figure out, well, what are going to be my 2 zeros that goes along with x squared plus 4. Now, depending upon what you remember, you'll see that this is relatively easy to figure out. So for here, if I was to allow this to equal 0, if I didn't remember the relationship in between what happens whenever I multiply complex conjugate numbers, then I would want to subtract 4 from both sides here. And then I notice that whenever I find the principal root, this will be plus or minus square root of minus 4. And of course, at this point, this lets me know that this is going to be an imaginary number. So this will be plus or minus square root of 4i. And the result of that would be that x is just plus or minus 2i. Okay, so that's one way of knowing that. The other thing that I mentioned is we know that whenever we have a complex number times its conjugate, one of the things that's always true is that a complex number times its conjugate always ends up being a real number, and that real number is of the form a squared plus b squared. And that happens because if we FOIL this out, we have the a times negative bi and the added to the a times bi. Those two terms tend to cancel themselves out to 0. Okay, and so what you see here is basically a x plus 2i times x minus 2i. Okay, so here this is just x plus 2i here times x minus 2i, according to what we see here, as well as that fact there. So saying all that to say that if we were to factor everything out, make it look nice here, then of course f of x is just essentially going to be 5x plus 1, x minus 1, and then x plus 2i times x minus 2i. So this is what our polynomial would look like if it is in factored form, meaning it's written as a product of linear factors. Now, the last thing that we need to do is sketch a graph of what this polynomial would look like. Okay, and so for that, we're going to go ahead and move on to the, I think I have the next page here where I have a XY plane for that one. So we'll go ahead and move on to that and sketch a graph of what this is supposed to look like. Okay, so we've moved on to the next page here, and we have our XY plane, and we see here that I've already listed what the 4 zeros are. And so whenever we are graphing polynomials in the real XY plane, one of the things I want to make sure that you understand is that we cannot see purely imaginary or complex numbers within the real number plane. So my point here is that whenever we fill out this little chart for multiplicity and all this, we'll fill it out, but the thing is we won't be able to see it on the graph. Okay, so when we look here, we see that we have a 0 at x equals negative 1/5. Of course, for all these, since all these factors only show up once, the multiplicity for all of these end up being 4. And since, the multiplicity of all of these end up being 1. And since all 4 of them end up being 1, then of course, they all will cross the x-axis. But for these last two, the concept of crossing the x-axis doesn't make any sense because I'm not going to be able to see it. So here, what I'll just do in this case is we'll just put not applicable here. Okay. And so if I was to graph this, let's say if I again had half of a unit for each division, then I know that at actually let's spread it out a little wider so that this would make a little bit more sense here. Well, not necessarily make sense, but it'll be a little bit more visual. So let's say every division is 1/5. So that means I would have a 0 right here. So let's see, 1, 2, 3, 4, 5. So this would be 1. 1, 2, 3, 4, 5. That will be negative 1. So this will be from negative 2 to 2 here. Just trying to draw it to where you can easily see what's going on here. And we have a 0 here at x equals -1/5, and then of course we have 1 at x equals 1. And that doesn't want to work for me, so I'm going to erase this and draw something, make it look nice here. That'll be the other 0. And so now, since both of these cross, we need to know what our leading term is going to look like. And if you remember, our leading term for this particular polynomial was 5x raised to the 4. And we know that x raised to the 4 looks like a lot like x squared, and x squared looks like this. So we know that our end behavior here is going to look like this. And so, seeing this, and I'm going to erase this. Ooh, nope, didn't want that to happen. All right, so let's try to clean this up, and then in this example here, why is this not working with me? All right, so I'm gonna pause this so that I can get rid of this so I don't waste any more time on it. All right, so now that we got the technology issues cleared up, if we look at our chart here, we know that since multiplicity of the -1/5 and 0, -1/5 and 1 zeros, our multiplicity is both 1, then we're just going to cross through the x-axis for each of them. And of course, from up here, if it crosses through, it has to go down. And then to get back up here and back up, it has to cross up like that. And so when we finally draw what this graph is supposed to look like, it's just going to look like a basic parabola. That's going to go through 1/5, come loop around here, go through 1, and then come back up like this. Okay. And of course, we could look at what our original polynomial x-intercept would be here, and we could just draw or put the point where that's going to be at. And for this particular situation, we had a -4 as the constant term. So this would actually be the point 0, -4 there. We're going to draw it. So this video concludes our examples of how we actually use synthetic division to be able to factor down our polynomials here. The very last thing I wanted to do is just take one example and show you how Descartes' rule of signs actually plays a role in all of this. And so I'll record that as a separate video because, again, you don't necessarily need to know that to be able to do what we're doing here. But for those of you that are interested, you can check out that. And so that will be our part 4 video.